Good morning, everyone. Thank you for joining us today. I have the pleasure of introducing Elaine Shi. She is a professor in Carnegie Mellon University. Her research interests include cryptography, security, mechanism design, algorithms, foundations of blockchains, and programming languages. She is a co-founder of Oblivious Labs, Inc. Her research on oblivious RAM and differentially private algorithms have been adopted by Signal, Meta, and Google. She is a Packard Fellow, a Sloan Fellow, an ACM Fellow, and an IACR Fellow. Without further ado, Elaine Shi presenting Oblivious RAM, from theory to large-scale deployment.
Thank you so much, Chelsea, for the introduction. I'm very excited to be here, and I love my hacker badge. Okay, I'll talk about Oblivious RAM, or ORAM for short, and the exciting story of how it evolved from theory to large-scale real-world deployment. So I'll begin with the Signal story and some other motivating applications in blockchains, and then I will tell you how to construct a simple ORAM algorithm, and then at the end I will maybe mention a bit more about applications in the blockchain space, and as well as like the technical roadmap going forward. Okay, so Signal has contact discovery, and they want to guarantee privacy for the users. So essentially in contact discovery, the user will upload its address book to the server, and the server will return the entries corresponding to his friends. So, but I mean, obviously for Vitalik, his address book is top secret, right? So he is reluctant to disclose it to the server. So how can we protect the user's privacy? A naive solution is to use encryption, like an encrypted database. So imagine the server is equipped with TE, trusted execution environment, or also called secure processor. So you can think of the secure processor as a hardware sandbox. Everything is always encrypted, and only inside the sandbox can things get decrypted. There is a decryption key inside the sandbox, so you can decrypt the data and do computation inside the sandbox, but any data that leaves the enclave, and the sandbox is also called an enclave, anything that leaves the enclave either in transit or in storage will always be encrypted. So you may think that this will solve the privacy problem, but as you sit down and think about it a little bit longer, actually encryption alone doesn't do very much to protect the user's privacy. And this is because when the enclave needs to do the computation, it needs to go to this database that resides in memory and on disk, and it needs to fetch those records corresponding to the friend. And which locations are being accessed will disclose exactly who your friends are. Okay. So this access pattern leakage is not just relevant for Signal. It's actually a pretty general problem. It manifests in many different ways. Like for instance, this is a binary search program. You don't have to stare at the code, but essentially what happens in binary search is that you will first look at the middle element of the array, and then depending on the result of the comparison, you either recurse on the left half or the right half. And now if you think about it, if you like observe the sequence of accesses, you can actually determine whether you are searching for a large value or a small value. Okay, and more generally, if your program contains control branches dependent on secret variable, let's say you are conditioning on the last bit of your secret key, and then depending on whether it's 0 or 1, the two branches exhibit different memory traces, then by observing what data is being accessed in memory, you can actually learn the last bit of the secret key. So this is an actual attack shown by researchers in UT Austin and Microsoft Research, and they show that if you are running off-the-shelf image processing software inside TE, and you can only observe the page-level access patterns, and these are like coarse-grained access patterns. And even such coarse-grained access patterns can allow you to recover the shape and the location of the objects. Okay, so the question we want to answer is, can we provably defeat such access pattern leakage, but we still want to preserve the efficiency of the program? So let me tell you a Signal story again, right? So there is actually a naive solution to solving this problem, which is every time I need to query the database for something, I'm going to make a linear scan over the whole database. And of course, a linear scan will hide which location I'm interested in. But the drawback of this approach is like, obviously, it is very expensive. So Signal actually did an optimized linear scan. They were like basically, for a batch of queries, they make a single linear scan. And even so, the overhead is linear. It's n over beta, where n is the database size and beta is the batch size. And back then, when they deployed the linear scan solution, they needed 500 servers, which was a lot. And eventually, they came around and they, realized that the right thing to do is to use an ORAM algorithm. So specifically, they implemented an ORAM scheme called path ORAM, which was proposed in our prior work in 2013. And once they deployed the scheme, they were down to 6 servers. So almost 100x saving in operational costs. And then asymptotically, path ORAM achieves log squared n overhead. But actually, in practice, one of the log has a large base. So really, in practice, you just observe log n overhead. Okay. And there are many other applications of ORAM besides Signal. Like, for instance, we are working with Ethereum Foundation to build ORAM into their infrastructure. Like, because Ethereum wants to enable private blockchain reads. They want to basically be able to provide RPC and full nodes, which allow users to privately access the public data that live on the blockchain. Meta has an implementation of our path ORAM as well. We actually don't know exactly what application they're using it for, but likely it's private AI. Flashbots is interested in using ORAM to enable private block building. And we are also collaborating with them. And it is hard these days to give a talk without mentioning LLM. So something that would also be nice to have is to have private LLM. Like, imagine you can query ChatGPT without disclosing your intentions and your query. So this is also something that ORAM can enable. And I also want to mention, in many of these applications, traditional databases completely fail. And the reason is because traditional databases only do encryption. They only encrypt the data contents. But for a lot of these application scenarios, like in Ethereum's case, the database itself is public. It is precisely the queries you want to hide, not the database itself. And in other scenarios, like in Signal's case, the database is not public, but it is known to Signal. So they're not worried about hiding the database, but they just don't want to see the user's address book. So in these cases, really what you need is ORAM rather than traditional encrypted database. Okay, so I hope this has got you excited about ORAM. So let's actually see how to construct ORAM. So in fact, ORAM is an extremely simple data structure, and I hope this talk can convince you, it is simple, and this is also the reason why it is so fast. So what is ORAM? It was first proposed by Goldrick and Ostrovsky back in the 1980s. It's an algorithmic technique that allows you to kind of quote-unquote encrypt access patterns. Of course, it's not really encryption because access patterns are a side effect of program execution. It is not like a data string. So behind the scene, what you are really doing is like you are shuffling and permuting the data in memory as you access the data. So we'll see how it works. If you want to think of ORAM as a box, as abstraction, essentially it will receive requests in the form of read some logical address or write to some logical address. And it will translate these logical requests into some physical accesses. And each logical request will be translated into potentially multiple physical accesses. And the ratio of the physical accesses over the logical accesses is essentially the overhead of the ORAM. And the security requires that no matter what your logical request is, the observed physical access patterns must be identically distributed. Okay, and then when we deploy ORAM, let's say in a secure enclave or TEE, essentially the ORAM is a client that runs inside this trusted boundary. It is part of your trusted computing base. Okay. So let me first give you the bigger picture of where we are in terms of like the theoretical landscape, and then I can tell you about the construction. So even back in 1987, Goldrick Ostrovsky already showed a non-trivial construction with log cubed overhead. So this is already much better than linear scan, right? But their scheme is very complex and it has large constants and it's completely impractical. So you wouldn't want to actually implement these log cube schemes. And they also prove that if you want an ORAM, log n overhead is necessary. So this is like a lower bound on the performance. So really what is interesting is like, on the practical side, we want to have an ORAM scheme that is practical, like not like the one by Goldrick or Ostrovsky. And on the theoretical side, we want to understand whether we can bridge the gap between the upper bound and the lower bound. So this is the research we have been doing, since around 2010, and we were able to answer both questions affirmatively, and we are able to construct a practical scheme which is now deployed in the real world at large scale, and we were also able to bridge this gap between the upper and lower bound. These two, unfortunately, they're not the same scheme. So today I will want to focus on the practical scheme. Okay, so I will tell you how to construct an ORAM. Before I tell you the idea, I want to just quickly brainstorm together. So a strawman solution is to just take all your data blocks and permute them in memory. So suppose the adversary doesn't know the permutation, right? So essentially every block is stored at a random location. In this case, if you want to, let's say, access logical address 9, you would just go to a random location. So it seems like this already gives you some security, but it is not highly secure. It is like not really secure if you need to access each block multiple times. Like, for instance, if I access the same block 9 twice, then it leaks frequency and linkability. So you can actually launch statistical attacks to infer which location is storing what data. And the reason why the strawman is not secure is the same reason why deterministic encryption is not secure. It leaks statistical information. So really, the moral of the story is that the blocks have to keep moving around in memory, because if they always stay in the same place, then anytime I access the same block multiple times, it'll leak statistical information. So this is the key insight I want you to keep in mind as I tell you what the solution looks like. Okay, so here's the solution. So ORAM is just a very simple data structure. It's a binary tree. In fact, actually, ORAM is even simpler to teach than the typical data structures we teach to our undergrad students, like red-black tree. It doesn't, for instance, it doesn't have complex balancing operations. Every bucket in the tree, every node in the tree is called a bucket. And the bucket has a finite capacity. It can store, let's say, constant number of blocks. And some blocks are real blocks. Real blocks are encryption of actual data, and some blocks are filler blocks, and filler blocks are just encryption of 0, and they're only there for security. They don't encode any useful data. Okay, so the most important invariant in an ORAM is that every block is assigned to a random path in the tree. So a path is like, a path from the root to some leaf node. So in this case, imagine the block at logical address X is stored on the blue path. And in the beginning, I'm going to cheat a little bit and imagine the CPU can store a position map that records where every block is. But in the end, I will get rid of the position map because this position map is very large and you cannot store it inside the CPU's cache. Okay, so reading a block is very simple because I just have to find out where the block is, which path it is on, and all I have to do is read this path. And then when I read this path, I can remove the block I want from the path and hold it in my hand, hold it in the CPU's cache. And at this moment, we are going to revisit that key insight I've mentioned. It is important that as soon as we read the block, we need to relocate it. Because if we don't relocate it, the next time if we want to read the same thing, we'll go back to the same path, and that leaks statistical information. So how do we relocate this block? The most natural idea is to assign it to a random new path. So I'm going to sample a path at random. Say I happen to pick the green path. And how do I relocate the block X to the green path? I will, the idea is like, where on the green path can I write the block X? Can I write it to the leaf? So the answer actually should be no, because if you disclose which path it is, then the adversary knows you have relocated something from the blue path to the green path, and the next time if you access the same thing, you'll go to the green path, and this still leaks statistical information. So really, you also cannot write this block to any of the internal nodes because these internal nodes leak partial information about the choice of the new path. So really, you have to write the block back without leaking what is the choice of the new path. And the only way to do that is if you write it back into the root. The root is on every path, so if you write it into the root, it satisfies the path invariant without disclosing which path I've chosen. Okay, so I mean, of course, you cannot keep writing things into the root. That will create a problem because the root will soon overflow. And how do we resolve? Okay, so before I tell you how to resolve this overflow problem, essentially, if you do this, the security of the scheme is very easy to see because anytime I want to make a request, I will just end up visiting a random path. And importantly, the choice of the path has not been revealed before because every time I relocate the block, I write it back to the root without disclosing the choice of the new path. Okay. So now let's try to resolve the problem I've mentioned, right? So because I cannot keep writing things into the root will soon overflow, and I have to overcome this problem. And in fact, there are actually two issues remaining. Like one is how do we resolve overflow, and the second is, remember I said I'm cheating. I'm assuming the CPU actually starts the position map that records where every block is, but we cannot do that because the position map is too large. So I'll tell you how to resolve these two remaining issues, and we will get a full ORAM scheme. So to resolve the overflow issue, we are going to introduce an eviction process. And the goal of the eviction, it's a maintenance process that tries to move things closer to the leaf. And if you do it in a clever way, you can prove that, except with negligible probability, no bucket will ever overflow. And in fact, in path ORAM, the way the eviction scheme works is every time I read something from a path, because I'm touching this path anyway, I'm going to use this opportunity to repack all the blocks on that path and pack them as close to the leaf as possible while subject to the path invariant. So in path ORAM, eviction and read are kind of like they take place on a single path. And this is why the scheme is called path ORAM. It's because every time I need to make a request, I just have to visit a random path in the tree. Okay, so that is eviction. I will not go into detail, but actually in the afternoon, I'm going to give a longer version of the talk, and I will go into the detail of the eviction in the longer talk. So let me also mention how to remove the position map, and the answer is just one word. It's recursion. Like essentially, you have this position map. You cannot store it in the CPU cache. You are going to recurse and store it in a smaller ORAM tree. And once you recurse logarithmically many times, your position map will be constant size, and at that time you can store it in the CPU's cache or registers. So essentially, every time you recurse, the size of the position map is constant factors, at least constant factors smaller than the original data set. Okay. So this is the whole algorithm, and it's really simple. It's just 16 lines of pseudocode, and even counting lines like and if and for. It's so simple you can print it on a T-shirt. And in fact, I guess the biggest debate in the ORAM community is not whether the ORAM scheme is simple enough or fast enough for practical purposes. It's more whether the tree is upside down or not. That is the most debated topic in the ORAM community. Okay, so just to summarize, how do we construct an ORAM? It's a tree-based data structure, and the key insights are a block is always remapped to a new random path whenever it is read. And then you must relocate the block to the new path without revealing the choice of the new path. And this is important for security. And in order to make sure the buckets don't overflow, we have to have a clever eviction process that tries to keep moving things closer to the leaf. And then the main work, like even though the scheme is simple, I want to say actually the proof of security, like the stochastic proof that there is no overflow, that is a rather complex and mathematical proof. Okay, so performance, so this is the performance we measure using our own implementation by Oblivious Labs. And we are using an Ethereum or Signal scale data set ranging from 100 gigabyte to 1 terabyte. And this is performance just on a single desktop machine. Every request, every key value lookup is only 20 to 50 microseconds. It's not even milliseconds. We are talking about microsecond level delay, right? So there's almost no delay, essentially. And then the throughput is very high, even on a single node. It can be up to 200K queries per second. And it's also easy for ORAM. It's actually very easy to do horizontal scaling by adding more machines. You can scale up the throughput proportionally to the number of machines. Our implementation outperforms Signal by roughly an order of magnitude. We outperform Meta by about 100x. And there is also this oblivious is a state-of-the-art academic implementation, and we outperform oblivious by like 600x. So I think this is probably the fastest implementation known to date. And I want to conclude with some more applications in the blockchain space and some of the ongoing work. So when do you need an ORAM? I guess like previously, what's interesting is like previously, people are using TEE a lot, but maybe they didn't realize that they need an ORAM. But in fact, whenever you need trusted hardware, you should actually think whether actually ORAM is needed. Because for a lot of computation tasks, they don't just linearly scan through memory. They are going to make dynamic memory accesses. And in these cases, chances are the memory accesses are leaky, and you would need ORAM. And also, ORAM is not just for TEE. Actually, if you want to have secure computation, like let's say TEE is replaced with a cryptographic secure computer enabled by multi-party computation, the same problem happens. And you need ORAM to make the accesses secure as well. Okay, so what are some of the applications for blockchains? I already quickly mentioned them at the beginning of the talk, but maybe I can go into detail for like one of them. Let's look at like Flashbot's application private order flow, and I'll explain why it's important. So, in blockchain, users submit transactions to the block builder, and the block builder will build blocks to be included in the consensus. So today, the transactions are submitted in the clear, and this creates this big problem called MEV, minor extractable value. And simply put, the block builder can front run and back run your transaction to make profit. And this is not only harmful to the user, it also creates a centralization effect for the blockchain. So in fact, if you look at Ethereum's ecosystem today, more than 85% of the blocks are mined by created by just two block builders. So essentially, it's a duopoly. Like the architecture is no longer kind of the decentralized architecture we used to think of, right? And this is why the stakeholders, they're really concerned about this problem, and they really want to mitigate MEV. And one way to achieve this is to add privacy to the order flow, to the transaction submission process. So imagine the users submit transactions in encrypted format, and the block building also happens in encrypted format without the block builder being able to see the transactions. And imagine you are going to execute the block building program inside the TEE. And the problem is that when you build the block, you have to speculatively execute the transactions. And I want you to think of the transaction as small smart contract programs. And as these programs execute, they're going to have to access data that live on the blockchain. And again, these accesses are highly leaky. They leak things like which crypto asset you are trading and the trading partners. And these are precisely the information you want to hide. So if you only encrypt the data and you don't obfuscate access patterns, there is very little privacy. Okay, so for this reason, we have been collaborating with Flashbots to try to demo the performance of private block building with ORAM. And in some ongoing work, this is a new ongoing work we are doing at our company. It's called Oblivious STL. So Oblivious computation also is not just about ORAM, because ORAM gives you a generic way to take any algorithm and compile it to an oblivious format. But oftentimes, if you have specific data structures or specific computing tasks like graph algorithms, you can convert it to an oblivious form without going through the generic ORAM transformation. And these customized oblivious algorithms are often faster than generic ORAM compilation. So in Oblivious STL, we are trying to make a counterpart of the STL library. Like think about C++ STL, right? This is like a standard library that's packaged with modern programming languages. Okay, so we want to create an oblivious counterpart of these common libraries. And this is ongoing work. We have already implemented some common data structures and maybe sorting and some graph algorithms, but there's a lot more to do to finish the library and increase the coverage. Okay, so finally, I want to conclude by asking the question again, do we need ORAM? And this is yet another large-scale application of ORAM, because if you come to my hometown, Pittsburgh, the coffee shops in Pittsburgh, they sell a donut called Oram. So do you need an Oram? Yes, because it's delicious. And if you come to Pittsburgh to visit me, I will definitely buy you an Oram. Thank you.
Thank you so much, Elaine. I just wanted to let you all know that Elaine will be furthering this talk in our workshop in the cryptocurrency community, which is in C101 at 2 p.m. today. And that will be for a much longer period of time with some workshops going on. So please come check us out at the cryptocurrency community. We hope you have a great day and a great con. Thank you.